Good morning, good afternoon, good evening, no matter the time from where you're watching this lecture video. I would like to welcome you to our class of Quantum Mechanics 1. My name remains Mr. Francis Lubangakene, a teacher for physics and mathematics. And here we go, get set and ready to enjoy and learn from this class. In this class, we shall be going through a number of course units. The course outline for this quantum mechanics 1 will go from the evolution of quantum mechanics, in which we shall be studying about the quantum effects, probability amplitude, and interpretation of wave functions, the superposition principle, the quantum principle of probability, expectation value, the Dirac's and the brackets notations, and others. So dear friends, we shall still go for wave functions, operators, definitions of an operator, and others. Yes, some of the reference books we need to take on would be that of the Amit Goswami, Quantum Mechanics. What I may recommend purely would be Noureddin Zetli, The Concepts and Applications of Quantum Mechanics, and also Feynman Richard P., Robert B., Layton, and Matthew, who wrote commemorative issues on quantum mechanics. Okay? That's how I recommend you reading these books. You may forgive me for my background is not clear, but I would love that we'd have this recording done. Thank you. Now, if I may begin, what do you think is quantum mechanics? What do you think is quantum mechanics? Like other mechanics, it is actually a branch of physics, yes, but which branch of physics are we talking about today? Which branch of physics are we talking about today as quantum? In relation maybe to classical mechanics and others, we have another branch of mechanics called quantum mechanics. So let's see what it is. Quantum mechanics is actually a branch of mechanics that deals with the mathematical description of motions and interactions of atomic and subatomic particles. That means this is the physics that studies the mechanics of the very small. How do they intermingle? How do they interact with energy? You know, physics is basically the study of matter as they interact with energy. So this time, the branch of physics we are calling quantum mechanics is going to study the interaction between the very small particles. We are calling them subatomic, like atomic and subatomic level. How do they interact, right? So you realize that this is in contrast with the classical mechanics, which is the branch of mechanics that deals with a macro study. Macro study means a study of an object at its whole setting, like the whole of a system of a mechanic, the whole of the universe, the galaxy, the spacecrafts, and others, probably the study of a macro existence. That's how do they interact with with energy. So that in that case, we shall be relating with classical mechanics. But here in this course unit, lecture 1 video, I would like you to concentrate on the study of the very small. How small is small? We are talking of the smallest being at a level of subatomic and atomic particles. You know what an atom is? And how about a subatomic, like an electron, like a neutron, like probably a proton? Yeah. How do they interact? Yeah. So that's what we are going to discuss today. Okay. All right. Now, in that relation, we need to know how these particles would be interacting. So if they may be interacting, then you realize that there is a level at which we study their freedom. So in this next slide, we're talking about the degree of freedom of an atomic particle. Yeah, what is the degree of freedom of an atomic particle? Yeah, in the attempt to study the interaction of those atomic and subatomic particles in their interaction with energy, you know, we need to know that there is a need to specify the exact position from which they are relating. We need to have a reference point. So for that case, having a reference point, we shall be able to tell the specific, and I mean the specific position of a particular or relative mass in that system, right? So if there is need to do so, then you realize that it is done through describing where exactly it is. We use coordinates to tell the position of a particular body. So since we are also using a 3D and 2D descriptions, you realize that the degree of freedom comes in how far away, how far away is this particle of a system from the x-axis, from the y-axis. So probably we shall be describing this in relation to the x and the y and the z axis. So we use the independent coordinates to describe the position of the mass in a system, right? So this description, we are using the independent coordinates to describe the position of a mass in a system, right, is what we are referring to as the degree of freedom of that subatomic or atomic particles. Thank you, friends. Stay tuned. So you realize that we bring in now the definition of what we are calling degree of freedom of subatomic or atomic particles. This is actually the degree of freedom of a particle is actually the number of independent coordinates which are used to specify the position of all the masses in that system, right? All the masses in that system needs to be specified, right? So by so doing, you realize that we need to use what? We need to use the degree of freedom. So the number of independent coordinates which are used to specify the position of all the masses in the system is what we are referring to as the degree of freedom. Thank you. So now in our next slide, you'll realize that we have the x, the y, and the z axis respectively, and they are independent. So if vx squared, vy squared, and vz squared are the square velocities in those respective axes, x, y, z in their order, then you realize that the mean square velocity written by v squared bar is just a summation of all those ones. I think we will borrow a leaf from the high school physics of thermodynamics, probably. That is the high school physics. The high school physics is what is giving us that in the classical descriptions of the thermodynamic system, right? So V squared bar will be a summation of those squared velocities, and that is what we are calling the mean square velocity, right? So since the particles are free to move in all the directions, you realize that it may be moving, probably may be moving with equal velocities in all the three dimensions, right? Therefore, suppose that we have our mean square, the square velocity in the x, the square velocity in the y, and the square velocity in the z is actually, they're actually all equal. That means that the average kinetic energy, is a half mv squared. That is in the classical way, where in 3 dimension we should have 3/2, that is 3/2 kBt. What is kb? K subscript b is the Boltzmann's constant, the Boltzmann's constant. So that is in the classical description. And still we borrow a leaf from our A-level what? Our high school classical thermodynamics descriptions, right? Where we use them, root mean square velocity and other things of thermodynamic system. Probably we used it in a gas, right? So this is where we come in. Now that we have a mean square velocity, now you know the half mv squared to be equal to 3/2 kbt, where I said kb is the Boltzmann's constant, and T is the temperature of that system or that particle. Okay, so now from equation 1, which we said that the square velocity in the x is equal to the square velocity in the y and the square velocity in the z, then you realize that the velocity, the kinetic energy of the body, yeah, the kinetic energy, actually the kinetic, averagely the kinetic energy of the body in both of the axes are relatively equal. That is what we're saying, that a half mv squared in the x equals the half mv squared in the y, then equals half mv squared in the z, which gives us a half mv, that is an average energy, half kb t, where we still use kb as the Boltzmann's constant, and this will give us the average, the average energy of that body in the 2-dimensional analysis, right? So you get it that the 2-dimensional analysis will probably have what we have it as a half kV, but the difference is that in 3 dimension, we have those 3 axes considered. So the degree of freedom would be like 3 in the 3 dimensions, and then 2 in the 2 dimension, and 1 in a single dimension, what? In the single dimension system. Now, our next thing is the equipartitioning principle of energy of a given system. If a system have subatomic and atomic level, and then there is interaction and we are studying that, then there is a principle that guides us, that equal partitioning, that means equal sharing, right? Let's go. For a system in a thermal equilibrium with its enclosure at any given temperature T, the average kinetic energy per degree of freedom is the same, right? Let's borrow a leaf from our our expression here, that the average kinetic energy per degree of freedom, yeah, this is what we're bringing. Per degree of freedom is here, right? The average kinetic energy per degree of freedom is actually the same. This is what I'm trying to round up with this orange line. Okay, so that is the principle of equipartitioning of energy, equipartitioning of energy, and this is the energy we are talking about. Thank you about that. Okay, all right. So if I may clean, let me first clean my space here. All right. Okay, so the principle of equipartitioning tells you that in a system which is in thermal equilibrium with its enclosure, which means the temperature or the state of the thermodynamics, the thermodynamic status of the environment is equals to the thermodynamic status of the system. So with that, you find that the body will be in thermal equilibrium, yeah, where the temperature or the heat transfer is zero between the bodies, the body and the environment. That is no transfer, neither from the environment to the body or the system, or neither from the system to the environment nor from the environment to the system. So that's what we are trying to mean by thermal equilibrium, right? So at that given temperature, the average kinetic energy per degree of freedom is the same. This statement is what we're calling the statement of the equipartitioning principle, right? So that statement there, that for a given, maybe I color it. Maybe I color that. I could be using a pen, right? I want to shade. If I could shade with some diamond. Let's check onto this. This that we are coloring here is what we are calling the statement of equipartitioning principle of energy, right? So that's great. What I would like to have noted clearly. Thank you. Okay. Now, what next comes here? In our status of studying system, we know that our system basically moves, and our movement is going to be in an oscillatory form. And that's why we are specifically going to study the back and forth movement, continuous movement, right? Repeated periodic movement. And that's what we are calling an harmonic oscillator. I hope you remember what an harmonic oscillator is from your lower physics. So if I am to think of an harmonic oscillator, then I would think of an oscillator which performs harmonic what? Principles. They follows the equations of descriptions and the principles of harmonic what? Oscillation, right? So now in that, let's consider a particle of mass m under the influence of restoring force. You know what a restoring force is? Yeah, the force that brings it back, right? As it moves down, then beyond the what? The mean position, there is that vibration. Beyond, actually, to the negative amplitude, back to the middle, and again to the positive amplitude. That's the restoring force. That is the negative kx. If we consider that to be the what? The spring, then it will satisfy the Newton's law of motion with a simple harmonic equation of the second derivative plus omega squared, where omega is the angular what? Angular velocity, and x is that displacement, right? That's great, displacement. And actually, if we think of x to be displacement, then the second derivative is our acceleration due to that motion, right? So I think that is what we are bringing on board. Okay, so x is the displacement from the equilibrium position, and then omega will now be k out of m, where m is the mass of that particle, and k is the spring constant, the elastic constant, right? So since xt, that is a function of time, right? Displacement is a function of time, which is equals to a sine omega t. Omega, we said, is an angular velocity. Angular velocity we could refer to as a frequency, right? So, I mean, angular velocity, sure. And then this is a sine omega t, right? Solving, we are bringing on board. Yeah. If you, sorry about that. Let me pick a pen. We are trying to say that this equation here solves that equation there, solves the simple harmonic equation with some given conditions, the boundary conditions at x equals to 0 and t equals to 0, considering A to be the amplitude of vibration. Okay, so if that is the amplitude of vibration, then you realize that the average energy of an harmonic oscillator will be the sum of the kinetic energy and the potential energy. And that sums up the mechanical energy that describes the state of the body, right? So the mean, oh, that is the mean energy of the body, or the total energy of the body, E, is referred to as the sum of the kinetic energy plus the potential energy. Remember that the kinetic energy, remember that the kinetic energy is given as a half mv squared, and the potential energy to be a half m omega squared x squared. So that is, we are still considering only one direction. Okay, let's consider only one direction or one dimension, right? So those are the kinetic energies we are going to consider. Now, where Vx is the mean square velocity, in the x direction, and then x squared is the mean square displacement, in the x axis. So we define it within one period. Let's study, we are narrowing down. Remember, we are studying the very small, so we should also study within the manageable very small. That is why we are defining it within one period. Yeah, one period is like from start to maximum, and we go. This is an harmonic one period. Yeah, like one wavelength. Yeah, that's what I try to mean. Okay. All right. Good. I'm just trying to erase and pick another pen and come back. All right. So you realize that now the mean kinetic energy is given by, I think this is also a formula that can be defined in mathematics. Okay. 1/period, the integral of that kinetic energy, actually, integral of kinetic energy. Yeah, in mathematics, we could talk of this as the inner product. We could also talk of this as the average. Yeah, so an average, this is the formula for calculating average. Okay, and again, we also apply it for potential energy, which is equals to the other way around. Okay, so we bring it up. We say that x equals to a sine omega t, and then dv dt, you know that, I mean, dx dt, you know that it is velocity, right? And then dx dt becomes what? Becomes a omega cos omega t. Therefore, Vx, that is the velocity in the x-axis, will be a omega cos omega t, and then the square of the velocity will be actual a squared omega squared cos squared omega t, so that x becomes, I mean, x as a function of time becomes a sine omega t, and then its square is actually a squared sine squared omega t. Right, let's dive into the calculation of the mean velocity, I mean the mean energy, the mean kinetic energy, which is an integral of kinetic energy itself. We have substituted the x. Yeah, we have substituted the x. Remember, we had here x squared. We had here x squared. Is it x squared or v squared? No, we had there v squared for what? For kinetic energy. Kinetic energy, we use v squared. Yeah, so this will be our v squared, because we have now v in the x, right? Remember, this is v squared in the x, right? The whole of this in the bracket is v in the x. So, and then we now pull out that v in the x outside. I mean, we will pull out all the constants. Mass of the particle is constant, amplitude of vibration is constant, angular velocity of the vibration is constant. We pull them out, and then that half is also constant. So we integrate cos squared omega t. You apply your mathematics of integration, but remember, we shall use the substitution as there appears on the screen. Then we substitute for cos squared omega t, having a half plus a half cos squared omega t. That's when we bring in this half inside here, and then we also multiply through there. So that again, it means we are going to pull out another half, causing a change here to make it a 4. And if that is already a 4, then we integrate the inner one partially, right? Because we say we shall integrate partially here 1, and then the other side will be 1 out of 2 omega sine 2 omega. Are we there? Sine 2 omega t. Then there we have it as a t plus a half omega, 1 over 2 omega sine 2 omega t, integrating from the lower limit to a upper limit. Okay, so you realize that when we integrate that, while keeping our constant out, right? So we integrate and substitute. When we substitute, this vanishes to 0. This also vanishes to 0 because, okay, any even coordinate, because here we are going to have a relationship between period and what and angular velocity. Period and angular velocity. What is it? Is it omega equals to 2 out of 2 pi out of t? I think that's it. That's what we're trying to use. 2 pi out of t. That's what omega is. If omega is the 2 pi out of t, then we substitute 2 pi out of t here. Substitute 2 pi out of t there. And when we substitute 2 pi out of t there, then it will cancel that, making it sine of 4 pi. So sine of 4 pi is actually a 0, like from your mathematics of integration. Okay, from your mathematics of integration, you realize that this is going to be a 0. This will vanish to 0, and the other one also vanish to 0. That means we shall only have ma squared omega squared out of 40 times t. There is this t here coming, and our final solution becomes that. So that means the average kinetic energy of a system or a particle undergoing harmonic oscillation, or the average kinetic energy of an harmonic oscillator, is actually mass of that oscillating particle, or mass of the system, times the square of their velocity, the square of the amplitude, and then the square of the angular velocity, or the angular frequency, and the square of it. So a half, Ke, average Ke will be m a squared omega squared out of 4. That's good. Let's go to the next class. You realize that now we need also to work on to the potential energy, the average potential energy, which is also equals to, is given as in the formula of calculating mean. So that you realize that we are going to integrate a sine squared omega t. Relating in double angle formula, we shall have double angle formula there, which is sine squared omega t. Sine squared omega t is giving us a half into 1 minus cos 2 omega. For that case, we substitute back. When we substitute, we shall still have our m omega squared a squared out of 4t into all this, right? Into all of this in the bracket. Then we integrate it and we get t plus 1 out of 2. It is a plus because integrating negative sign is already, negative cos is already a positive sign. But here should be 2. Here should be a 2. How can I edit? There should be a 2 here. This one is not. Let me have a pen. I will have to write there that we need to have this to be sine. This is sine of what? Sine of 2 omega t. The one down here should not be only sine omega t. No, it is 2 omega t. Just like it comes from this point here. Okay? So sine of 2 omega t. That's great. So let's proceed. When we integrate there, you realize that this one will still vanish to 0 by substituting. There is still 2 omega t. Yeah, this one is 2 omega t, which will still come back. This one here, let me align with a different color. This blue shaded thing here, when I shade this one blue, that means that blue is sine of 2 what? 2 omega capital T. That is what I'm trying to mean there, sine of 2 omega capital T, not sine of omega T. I think that was a typo. Good. Let's proceed now. Let us proceed with what we have here now. All right. So what I have here is that the average potential energy is actually equals to the average kinetic energy. If you see the results of the average potential energy down here, yeah, that side to the right of my screen, you'll realize that, okay, this thing is equal. But now, what guides you as a question? When I want to set this question to prove that the kinetic energy is the same for an harmonic oscillator, then I will tell you to show that the average KE and the average PE of an harmonic oscillator are equal, given X of T. This one is a T. X as a function of time. X as a function of time. This one here, yellow in the question, is a T, not X. X as a function of time equals A sine omega T. So solves the kinetic equation with the restoring force equals negative Kx. K is the first constant. Yeah, it is the first constant. I mean the spring constant. And X, I mean A here in this case, A is the amplitude of vibration. So there comes our discussion point. Okay? If you want to answer the other question, we need you to work along with that question. All right? Thank you. Now, what do you know about the oscillating mode or the oscillator's mode, right? When we consider a one-dimensional vibrating and stretching string, assuming that the string is damped at one end, that means there is a limited length under study. Each end from x equals to 0 up to x equals to L. That means the length that the string is of length L, right? So the displacement function uxt, that is the displacement with respect to time, satisfies the wave equation, which is the second derivative equation of wave, right? I hope we are familiar with this wave equation. If not, we derive back, okay? And we shall still work with that. So the boundary conditions tells you that at x equals to t, then we shall have u, the displacement function equals to 0. And then delta, okay, the first derivative with respect to time of that displacement function, actually velocity is equals to 0 at t equals to 0, right? So let u of xt be a double function of x and of x as a function of x and t as a function of time. All right. Then you substitute for u. We are substituting for u. Remember, we are up there. Let me first erase some part of my presentations here. Good. Now, when we go back here, we realize that there is a second derivative of displacement function. So that displacement function here is already being taken to be a product of two functions, displacement function and a time function, okay? So we substitute them here in the place of uxt, wherever there is uxt, we substitute that function we have let up there. So for that case, we do their second derivative. And then we shall solve by separating variables. while we divide through by xt so that we can separate their variables. And you realize that we come up to the level of 1 out of x d2x by dx, which is equals to d capital 2x, d2 capital X by dx squared, which is equals to a half v squared t d2t out of t squared, which is a constant, right? If a displacement function is equals to time function, how can time be equals to displacement? Time cannot be equals to displacement unless they are a constant. And that constant, we take it to be a negative k squared. This is tactical, yeah? I'll take you to partial differential equations. We go and solve it using the knowledge of partial differential equation. Without physics, there is no mathematics. So applying that, we shall realize that we take one side, that is d2x by dx squared plus k squared x equals to 0, with x at 0 and x at L equals to 0. Those are the boundary conditions. Then we have it substituted from this, and also on the same case, the first derivative of that time is also equal to 0. The time with respect to time, the time function with respect to time here is also equal to 0, and dt is actually equal to 0. So we assume a solution of the form x equals to a s sine kx plus b cos kx. That is to say, the displacement function at x equals to 0 is actually equals to a sine k0 plus b cos k0, which means this is equal to 0, and thus b is equal to 0 and x of x equals to a sine kx, and that is the solution we are talking about. Okay, so on that occasion, now you realize that x at L, right? If x is already equals to L, so what do? We substitute L everywhere where there is x. So we find out that the displacement function is actually equals to 0. If the displacement function is 0, but amplitude is not 0, so sine KL is going to be equal to 0, because if two functions are multiplying themselves and the result is making a 0, right? Then that means one of them should be a 0. And now we are saying amplitude cannot be 0. That means sine KL must now be a 0. So for that case, we shall have, what are the values bringing sine of a given angle, giving it a 0? Okay, that means it is any numerical coefficient of angle pi gives a 0. That means KL actually equals to n pi, and that is K equals n pi out of L, where K is the what? K is the constant. K is the spring constant of that oscillating body. So if n is the numerical what? Numerical coefficient of pi, like 2, 3, 4, 5 pi, yeah. So all those are zeros. Therefore, it is n pi out of L, where L is the length of that oscillating body. Now we have it as x. We now substitute back because now we know the value of K. We now substitute back in the displacement function. We have it as x of x is now equals to a sine of n pi out of L of x. Now we assume a solution of the other one again, the other side. Again, we take that solution. Then we differentiate it first time and we equate that differentiation to 0, right? Because we said dt, d capital T by T is actually equal to 0. So we need to first differentiate this one with respect to time, and then we equate it to 0. So for that case, you realize that at that time at T equals to 0, at the starting time T equals to 0, d capital T by T is also 0. Thus, the whole of this one is a 0. Okay? And this means that if that is a 0, you can check. C cos of what? C cos of 0. Okay, that means because this one will vanish and we shall have C to be equals to 0. Okay, because we shall have our 0 equals to CVK. CVK. We shall have our our 0 equals to CVK. You get that? If 0 is equal to CVK, then we divide both sides. Then you find that C is actually equals to 0. Now, if C is 0, okay, if C is 0, now we substitute back in the time function. Then we have our solution sorted. Because what we are looking for generally, what we are generally looking for is just the solution of u of xt. u of x, u of xt. Okay, we are generally looking for u of xt. With that, we said it is a function of, it is a product of a certain function which is in a displacement. Yeah, product of a certain function which is in a displacement times that function which is in time. It is a time function and product of time function and what and time function and a displacement function. So on that case, you realize that in that case you realize that what? Okay, in that case you realize that we have our function already. Yeah, we already have our function. Check at this. I am going to color red. I'm going to color this function here red. There's a function that we already have, and we are going to have it colored red. We already have our function in displacement. There, which is going to take for us that one. Okay. Yeah, it is going to take for us this one. Then we now have our C equals to 0. That means we are going to substitute this one. I mean, we are going to substitute C back into this equation because here is now 0. And then now we have our T of T equals to D cos of N pi V because we have already got K as N pi out of L. So we also now have our what? Our function there. Okay, so if now we have our function, then we can rewrite now the general wave function that solves the equation. That solves the wave equation. Okay, so what we're looking for is to go solve the wave equation, and that function which solves the wave equation is u xt, which is given as a double function product. Okay, so thank you. Now you realize that let me clean my board. I clean my board in all ways possible. All right. Okay. Now you realize that since UV is already got, I mean UXT is already got here, then we find that this is AD sine of N pi out of LX cos of N pi V out of LT, which is also given as C prime, and C prime is the general constants here, the general amplitudes of vibration. Okay, so where KX is NX, this one now we are taking one direction. We're taking now one direction. These numerical values are in one direction of the x, yeah, those numerical values, and then the angular velocity is also in one direction of the x. And so we shall have kx as omega out of v, and then 2 pi f out of lambda, out of lambda f. What is lambda f? Lambda f is, that is from wave function, right? Wave equation, v equals to lambda f, and then omega equals to 2 pi f. So we substitute them there. And then this we shall equate to K. K, which is N pi what? K, which is N pi out of L. This one we are lacking our L. Okay. This one we are lacking our L here. Let me have a pen and we write something in there. Okay. Let me have a pen, not a pointer. Good. Here we should divide by L. If we divide that by L, then we do what? We now multiply both sides. I'm trying to bring it as 2 pi. 2 pi out of what? Out of lambda. Okay? 2 pi out of lambda equals to n in the x out of L times pi. And this pi will go with the other pi, and then we multiply both sides by L to give us n equals to 2L out of lambda. And that is what we call the number of acceptable mods. That's what we are looking for. The number of acceptable what? Mods. The number of acceptable mod is now given. N, I repeat, N is the number of acceptable mods of that harmonic oscillator. Okay. Yes. So that acceptable mod is just given as nx, that is acceptable mod in the x direction, is given as 2L out of lambda. The derivations we did prior, and if you have some shortcomings or some challenges in, you may still need to visit back. Okay. So then, on that case, we extend this idea to the cubical volume now, so that we have now the three-dimensional what? Analysis now. So A sin kx, kx in the x, sin ky in the y, and then sin kz in the z cos omega t. Yeah, that is the u function here. The u function in x, y, t. I think this is what we're trying to bring. U of x, y, z, and t. This t here, this t is the time function. Then the others, this one is now the general amplitude. Then these are now the constants, the spring constants in those respective directions. So the boundary conditions will be u equals to 0 for x equals to 0, x equals to L, y equals to 0, y equals to L, and z equals to 0, z equals to L. Those are the boundary conditions. And now gives us the rise to calculate. And by the way, we are just substituting now, giving us kx equals to the acceptable mod number times pi in all of the respective directions. And we give k squared to be defined as the mean what? I mean the square spring constants. And this will mean we are squaring pi out of L times the square of all those acceptable mods in the respective directions. Now, if the square of those ones also, where nx are the positive integers of those acceptable mods, then we shall have what? By the way, even if we square negatives can still neutralize, not so? That's great. Now that we have those, then we have now the general or the total acceptable mod in all the three dimensions will be the summation of those squares, the summation of those squares now, so that we have our n squared to be n in the x, n squared in the x, n squared in the y, n squared in the z. Those are the summations. Then the general spring constant k squared will actually be, we substitute, right? We substitute. Remember, we have k. K squared is here. And k squared, right? We have k. K squared is here, and it is a square of pi out of L times that square of the what? of the acceptable mode numbers. So those cases we bring down here, then we substitute for the acceptable mode numbers, and still k, we have the value of k equals to the other one, then the acceptable mode number will be a root of 4 pi squared out of that. That means, okay, the allowed wavelength lambda will also surface there, and then we have acceptable mode to be equals to 2L out of lambda generally. Okay, so now in the whole of this class, what have you learned? As a summary, in this class, as we close, we have learned about the introduction to the term quantum mechanics, where we said that it is the study of the very small. It is actually the branch of physics that deals with the interaction of matter at subatomic and atomic levels as they interact with what? With the energy. We realize that there is something we are referring to as the degree of freedom, the number of those independent coordinates that we use to define the position of those particles at those various levels. And then also we studied the kinetic energy in 2D and 3D with a reminder of the high school mathematics, physics. Then we also studied the equipartitioning principle of energy. Then we had also the total energy in an harmonic oscillator, where we found that actually the potential energy, the mean potential energy and the mean kinetic energy are equal. Okay, then we studied also the modes, the acceptable modes of an harmonic oscillator. Remember, we studied all this from number 1 up to number 3 in this video, lecture 1. Then we also have the allowed wavelength of an atomic and subatomic particles. Members, thank you for attending our class today, and I would like to ensure that we meet again in the next class. In the next video that we shall be making. Okay, so thank you. Don't forget to make any inquiry through all our virtual platforms. I remain your teacher, your lecturer, Francis Lubankeni. Come again and follow us for more.